So hello, everyone. My name is Tao Wang. I'm a PhD student in UMass Amherst. And so it's my pleasure to introduce you the GreenFunc package we developed, which is a powerful tool for solving complex quantum many-body problems. And this work is done in collaboration with Kun Chen, Pengcheng Hou, Xiansheng Cai, and Zhiyi Li. So in the most general sense, so a Green's function describes a response at the coordinate x2 and time t2 with respect to a source at x1 and t1. And so a typical example would be the sound wave shown here. And so in the many-body physics context, this would correspond to creating a particle at x1, t1 and detecting the particle at x2, t2. And so almost all experimental observables are Green's functions. And so several properties of the Green's functions make it numerically challenging to handle. So the first one would be the multidimensionality. This is because we can have n particles involved in the process, which creates multiple sources and responses. And so the second property is singular analytical structure, which basically originates from long-range correlation either in space or time. And typical example is a Coulomb interaction. So since Green's function is a single value function on space-time variables, so it's natural to save it as an array on discretized meshes. And so this leads to the core structure in our package, which is the mesh array shown here. And of course, to overcome the challenges I mentioned before, we still need to use efficient meshes that's specialized for different purposes. And this is generated by 3 other packages we developed, shown in the right column. So the first package is the composite grids. So the idea behind this package is that, so typically physics behaves differently at different length scales. For example, here we can have water molecule droplets and waves. And so this leads to also multi-scale behavior Green's functions. As an example, here we have a Green's function which is mostly flat, but it's exponentially sharp at the around point 1. And so to capture this behavior, so we use composite grids, which is basically panels divided into subgrids. And so here we have the first layer as a panel logarithmically dense at point 1. And which is showing the blue box. And then in each panel, we have a quadruple subgrid, which is a barycentric grid that enables the high accuracy interpolation. And so for more complex Green's function, you can always use a nested structure by replacing the subgrids with a composite grid. And so here is an example code for generating the Green's function shown here. And the second package is the Brilliant Zone meshes. So this is developed for crystal. So most solids in our nature are crystals with lattice structure that has discrete translational and point group symmetry. And so due to the translational symmetry, one can just consider the unit cell, which is, for example, in this triangular lattice shown as the hexagonal. So one special type of the unit cell is the Wigner seed cell, which has the same point group symmetry. And in momentum space, that would just be the Brilliant zone. And so one can further reduce the calculation to just the irreducible wedge of the Brilliant zone by making use of the point group symmetry. That would be the red triangular shown here. And so in 3D, that would be a significant reduce since the fraction would be much smaller. And so here is an example of the 3D irreducible wedge generated by our package. And so this would be an example code. So of course, we also equip the Brilliant Zone with a meshes shown as the yellow points here. And so the third package is specially developed for Green's function. So as one can see in this figure, so the Green's function in the imaginary time space typically has very singular behaviors. However, it is proven that one can make use of the universal structure, so-called lemma representation, to identify a discrete set of grid points, which can be used to reconstruct the whole Green's function up to any given accuracy epsilon. And these grid points are universal in the sense that for a given epsilon, it only depends on whether you have fermion or boson. And so this is called the discrete lemma representation, or in short term, DLR. And so for a given temperature T and epsilon, the number of grid points required is scales as log 1 over T and log times log 1 over epsilon, which is typically just hundreds of points when you have very low temperature at 10 to minus 4 Fermi temperature and very high accuracy at 10 to minus 10. And so the package also enables very fast and accurate Fourier transform and interpolation, which outperforms the standard uniform grids with the fast Fourier transform. And so here we show a example of our interface for performing the Fourier transform and interpolation. And so with all the packages we developed, we were able to study two outstanding physics models with unprecedented accuracy and efficiency. So the first one is the so-called SYK model, which was first proposed as a as spins with all-to-all random couplings. And this is both related to condensed matter physics, such as strange metal and high temperature superconductivity. And it's also connected to black hole physics by the so-called holographic principle. So before this was typically by conventional method can only be solved down to like 10 to minus 2J. However, with our package, we were able to solve the whole problem with just this one page of code down to 10 to minus 14. And so these are basically the for the experts, the diagrams that we need to solve. And the next problem is the ultra low temperature superconductivity. So basically, many superconductors in nature has extremely low temperatures, such as this nice picture with bismuth in from Wikipedia, and so it can be as low as 0.0 millikelvin. And so it would be extremely hard to resolve with conventional numerical method due to the high computational costs. However, so with our packages, we were able to extract the superconducting phase diagram for the uniform electron gas with the lowest transitional TC as 10 to minus 200 Kelvin. And so finally, I would like to advertise that all the packages were developed under the numerical effective field theory, and which we have the ultimate goal of developing the quantum field theory for electronic structures. And so please feel free to ask any questions and also explore our packages and submit any issues to our. Thanks.